In this unit, we will be covering the basic concepts of DC machines. This unit will be covered in three parts. We know that a machine is an assembly of components with a predefined purpose so as to decrease the human effort. When this machine involves electricity, we call it an electric machine. Electric machines are mainly classified into motors and generators. A motor converts electrical energy to mechanical energy, whereas a generator performs the reverse function. That is, it takes mechanical energy and converts it to electrical energy. In this unit, we will be covering the basic concepts of DC machines. We will start with the working principle of DC motor. Thereafter, we'll go to the working principle of a DC generator. Once we understand the working principle, we will be able to better appreciate the constructional features of a DC machine. Then we will take up the circuit model, EMF equation, and torque expression for DC machines. Based on the type of connections between the windings, we will see the types of DC machines, and finally we will discuss their applications. So in this part, we will start with the working principle of a DC motor. The working principle of a DC motor is based on an already well-known principle that a current carrying conductor, when placed in a magnetic field, experiences a force. Now, the direction of this force is given by Fleming's left-hand rule. We all know this rule. According to this rule, you need to extend your thumb, your first finger, and your middle finger of the left hand in such a manner that they are mutually perpendicular to each other. Once you do it, then the direction of the middle finger corresponds to the direction of current. The direction of first finger corresponds to the direction of magnetic field. And once you know these, the direction of force is determined by the direction of the thumb. To explain the working principle of a DC motor, we will take help of a very simple arrangement. In this arrangement, I have taken a permanent horseshoe magnet, which means that it has a south pole and a north pole. Due to these poles, a magnetic field will exist inside this area under the magnet, such that the lines of force are from north to south outside the magnet. Now, inside this field, I have placed a coil which is free to rotate about this axis. I have also marked the end points of the coils so as to identify the conductors. So we see that we have two conductors here, AB and CD. Now we give electrical energy to this coil by supplying a current through it. The current is such that it enters at A, and in the conductor AB it flows from A to B, while in the conductor CD it flows from D to C and then it comes back. So we have a condition here that these two conductors are carrying current and they are placed in a magnetic field. So both of them should experience force. Let us determine the direction of these forces. So what we do here is we see these conductors from this point, and for conductor AB we see that the current is moving away from us. That is, if we take this plane as the reference, then this current goes into the plane. The field is from right to left, so I have shown here as right to left. And now if we apply Fleming's left hand rule, we see that the force will be upwards. So I am showing this force here, which is upwards. Similarly, for this conductor CD, we see that the current, when we see from this point, the current comes towards us. So in this plane, we have marked it with a dot. The direction of field is again from right to left, and here also when we apply Fleming's left hand rule, we see that this conductor experiences a force which is downwards. So I have marked this force here in downward direction. Hence, these two forces will create a torque which will be clockwise in direction. So this is how we are converting this electrical energy to mechanical energy. This motion will give mechanical energy. However, we see that once this coil rotates, the position of the conductors will change. In this case, this conductor AB is under the south pole, whereas the conductor CD is under the north pole. Once this coil rotates, we see that the conductor AB will come under the north pole, whereas the conductor CD comes under the south pole. So let us determine the directions of forces in these two conductors in this condition. So for the conductor AB, we see that the field is from right to left, and when we are seeing the conductor from here, we see that the current is moving away from us. So in this plane, we have taken it flowing into the plane. Now if we apply Fleming's left hand rule, we see that the force will be upwards. So the force in this conductor AB will be upwards. Similarly, for the conductor CD, once again the field is from right to left, and when we see it from here, we see the current to be coming towards us, which I have marked here also. Again, if you apply Fleming's left hand rule, you see that the force should be downwards. Hence, the force in this conductor should be downwards. So these two forces will create a torque which happens to be anti-clockwise here. So I am showing both the cases. In one case, we have the conductor AB under the south pole and conductor CD under the north pole. In the second case, when this coil rotates, we have this conductor AB under the north pole and the conductor CD under the south pole. So the direction of current, of course, it remains the same, that is from A to B and D to C. Here also it is from A to B and D to C. But we see that in one case the torque is clockwise, whereas in the other case the torque is anti-clockwise. So the torque here is changing its direction, which is not we want. We want a unidirectional torque so that the rotation of this coil is unidirectional. So here our purpose will be served if we can reverse the direction of current when this conductor AB is under the north pole. That is, in this case, if the current is from B to A in the conductor AB and from C to D in the conductor CD, then again this torque will remain clockwise. Once again, when this conductor AB comes under the south pole, the direction of current should be from A to B. So we need a mechanism which can periodically change this direction of current. That mechanism is known as a commutator. It is a very simple mechanical arrangement which I have explained here. What we do is that we take a copper ring and we cut it from the middle. So I get two parts of this ring here which we call as segments. So this is a segment S1 and this is a segment S2. Now what we do is we join these two segments again, but with an insulation between them. So this is an insulation, which means that the current cannot flow from S1 to S2 or from S2 to S1. Now, this commutator with its two segments and the insulation between them is connected to the coil. So here what we have done is we have connected the coil to this commutator in a manner that this conductor AB is connected to segment S1, whereas this conductor CD is connected to the segment S2. Whenever this coil rotates, this commutator also rotates. So the commutator is also a rotating part of the machine. Again, I am showing the poles here. So I'm assuming that this conductor AB is under the south pole and conductor CD is under the north pole. Now, to give electrical energy to this coil, we take two brushes which are in touch with the segments of the commutator. These two are stationary parts. I have called them as brush B1 and brush B2. These are made of carbon. The DC supply to this coil is given through the brushes and commutator segments with a DC source. Now this arrangement helps us to achieve the purpose of a unidirectional torque. So in the first case, when this conductor AB is under the south pole and the conductor CD is under the north pole, let us see the direction of current. So this is the higher potential terminal. The current enters brush B1, then to segment S1, then it goes to the conductor AB, flows in a direction from A to B, and in the conductor CD, which is under the north pole, it flows from a direction D to C, then it comes to the segment S2, then to brush B2 and back to the DC source. So in this case, we know the direction of the two forces and the resulting torque, which is clockwise in nature. Now what happens is, once this coil rotates, this commutator also rotates with the coil. Now you see carefully that with brush B1, the segment S2 is in contact, whereas with brush B2, the segment S1 is in contact. Also, the conductor AB is now under the north pole and CD is under the south pole. Let us see the direction of current. So this is the higher potential terminal. Current flows to the brush B1, then to segment S2, and then it flows to the conductor CD in a direction C to D, then in the conductor AB from B to A, then it comes to segment S1, brush B2 and back to the source. So here we see that when the conductor AB changes its position and comes under the north pole, the direction of current is also reversed. In the first case, the current was from A to B, whereas in the second case, the current is from B to A. And hence, what happens is the torque generated here will again be clockwise. So this is how we will achieve a unidirectional torque with the help of a commutator, and the coil will rotate in one direction. So this explains the working principle of a DC motor, and this also helps us to identify the main parts of a DC motor. Now, when I was talking about a permanent horseshoe magnet, the actual magnet is not horseshoe and it is not permanent. We take help of a DC supply and we make an iron core into an electromagnet. So this first winding, the purpose of which is to create a magnetic field, is called the field winding. The coil that I was showing here, to which we were supplying the current, is a single coil, but in actual machine it has multiple coils, which makes it a winding, and this winding, which is rotating in nature here, is called armature winding. And of course, the third part is the commutator, which in this case was converting this supplied DC into an AC inside the armature winding. Of course, in an actual machine, the construction is a bit different, although the main parts are the same. So we will discuss construction in a detailed manner, but just to show the briefly the constructional parts, I have shown these two figures. So the poles, multiple poles are shown here, and this copper winding that you see is the field winding. The commutator and the armature winding both are placed on this shaft. The armature winding, of course, it is a distributed winding placed inside the slots, which we will discuss later on. So this is how the construction of a DC motor will look like. So in the next module, we will see the working principle of a DC generator.